to introduce you once again, ma'am. On behalf of the department and on the behalf of all the participants and on my personal behalf, I would like to welcome our today's guest, our expert speaker of the session, Dr. Anuradha Gupta.
प्रवीण जी आपकी आवाज नहीं आ रही। Can you hear me?
On behalf of all the participants and on my personal behalf, I would like to welcome our today's guest, our expert speaker of the session, Dr. Anuradha Gupta. However, all the participants are already well aware about ma'am, but it's my foremost duty to introduce you once again, ma'am. Dr. Anuradha Gupta is an associate professor at Department of Mathematics, Delhi College of Arts and Commerce, University of Delhi. BA Honors Mathematics from Janki Devi Memorial College, University of Delhi. MA Mathematics from Hansraj College, University of Delhi. Ma'am has completed MPhil and a PhD from University of Delhi. Her specialization areas include operator theory, functional analysis, and fixed point theory. Experience of over 30 years in teaching and research, Dr. Anuradha Gupta has published more than 60 papers in various journals of international repute. Ma'am is a reviewer of various reputed international journals and also authored 4 books. Ma'am has delivered numerous invited lectures in various national and international conferences across the world, such as Romania, Austria, USA, and Turkey. Dr. Anuradha Gupta has delivered various lectures on Vedic mathematics and conducted various workshops on the topic Vedic mathematics. Ma'am has undertaken a research project funded by UGC. Ma'am has organized various summer schools at University of Delhi. Under her supervision, 10 students have completed their PhD, and right now 6 students are pursuing their research work under the supervision of Dr. Anuradha Gupta. Without much delay, I would like to welcome you, ma'am, to deliver today's expert lecture. Ma'am, please, over to you. Ma'am.
Thank you, Praveen ji, for nice introduction. Is the screen visible to you?
Yes, ma'am.
I once again thank JC Bose University and the Department of Mathematics for giving me this opportunity to talk on various topics on complex analysis. Today's topic, calculus of residue, it is quite fascinating. Fascinating in the sense that it gives us methods for finding the integration, definite integration, as well as the integration along the closed contour. And contour, I think you know, this is nothing but the join of finite number of straight lines and curves. Means that if we have this type of figure, then this is a closed contour. I think now you are aware about the Lorentz series expansion. So we have that if let f be an analytic function in the punctured disk d dash, this is the set of all those complex numbers such that 0 less than mod z minus a less than epsilon. Now, what is the meaning of puncture? That if we have a disk with center a and radius epsilon, then there is a hole at this point a. Means at the point a, the function is not analytic. Everywhere around a, in the neighborhood of a, the function is analytic. So that is why this is isolated point, because the behavior of all other points in the neighborhood of a is same except this point A. So this point A, this is left in isolation. That is why it is known as isolated. And since it is the function is not analytic at this point, so this is known as isolated singularity. So then it has Laurent expansion about the isolated singularity at A. And what about this Laurent expansion? This is z minus a square, z minus 1, z minus a, c naught, c1 into z minus a, c2 into z minus a square, plus c3, z minus a cube, and so on. This is the Laurent expansion. So we define residue of f at the point A. A is isolated singularity as the coefficient of 1 upon z minus a. Means this a z minus the isolated singularity. And if you just observe from this Laurent expansion, this coefficient is nothing but c minus 1. So whatever coefficient we get in the Laurent expansion, this is known as the residue. For example, if we consider a function fz, which is sine z upon z raised to the power 4, you can see that the denominator vanishes at z is equal to 0. So z is equal to 0 is an isolated singularity. If you just expand sine z, what is this? This is z minus z cube by 3 factorial plus z5 by 5 factorial and so on. When you divide it by z4, divide by z4. So what are you getting? You are getting this to be 1 upon z cube minus z square by 3 factorial is 6. So this is 1 upon z. This is 1 upon 6z, then plus z upon 5 factorial and so on. Here, the isolated singularity is 0. It means we want coefficient of 1 minus z minus z, 1 upon z minus 0, which is 1 upon z. So you can see from this expansion, the coefficient of 1 upon z is nothing but minus 1 by 6. Therefore, the residue of f at the point 0 is nothing but minus 1 upon 6. So simply we have to take for the residue the coefficient of 1 upon z minus the isolated singularity. Shall I erase this, Praveenji?
Yes, ma'am.
Now you must know there are 3 types of singularities. First is removable singularity. Removable means that if you just remove the point where it is singular, it becomes analytic everywhere except that point. So that is why it is known as removable. Second is pole, and third is essential singularity. As I have already explained, that residue can be found at the singularity. So obviously, corresponding to these three types, we have different formulae. So let me explain you in short the formulae for finding the singularity. Now, one more thing before I proceed, I want to uh, tell you the formula which can be used using the Laurent expansion in finding the integration. So what we say that the residue of f at the point A, this is nothing but 1 upon 2 pi integral along C fz dz. This is the definition. This is residue of f at A. Now, first formula is using the Laurent series. Now, for example, the function is fz is equal to 1 upon z into z minus 1 whole square. And we want to find residue of f at 1. But you can see that this is 1 upon z, right? So we have to convert this. You can write this as z minus square, z minus 1 plus 1. So further, this can be written as 1 upon z minus square. This is 1 plus z minus 1 raised to the power minus 1. By binomial expansion, if you just expand it, you are getting this to be, because this is minus 1, so alternatively we will have plus minus. If you just open, this is z minus 1 whole square minus 1 upon z minus 1 plus 1 minus z minus 1 and so on. So we want to find out the residue at the point 1. It means we want to find out the coefficient of 1 upon z minus 1. So what about the residue of f at the point 1? Just check the coefficient of 1 upon z minus 1 in this series. So you can see this is minus 1. So therefore, this is equal to minus 1. This is the 1 upon z minus 1. Its coefficient is minus 1. So this is the residue. Now, for example, you have that if the function is e raised to the power 3 by z and find the residue of f at the point 0. You know the expansion of e raised to the power z? It is 1 plus z square by 2 factorial, z cube by 3 factorial, and so on. So what about e raised to the power 3 by z means you need to replace z by 3 by z. So 1 plus 3 by z plus 3 by z whole square, 1 by 2 plus 1 by 6, z 3 by z whole cube, and so on. So basically, we want to find out the residue of f at the point 0, which means that coefficient of 1 upon z minus 0, which is 1 upon z. So what is the coefficient of 1 by z here? It is 3. So you can see that this is equal to 3. So finding residue is not a difficult task. But if suppose that we have a simple pole, the second formula, the first formula is using the Laurent expansion. Second is for simple pole. So it is residue of f at the point A. This is nothing but the limit z tending to A. A is an isolated singularity, which is a pole of order 1. So this is z minus a into fz. For example, that we want to find out the residue of, okay, before I want to give you one more formula so that one joint example can be given. If your function simple pole, there are two formulae. First is this, and the second formula for simple pole. If the function is a rational function, means your function Rz, this is of the form Az upon Bz, with the condition that A at the point A is not equal to 0 and B at the point A is equal to 0, means denominator vanishes at the singularity. So what we do, in this case, the formula becomes for finding the residue of f at the point A. This is, you just substitute A, the isolated singularity, in the numerator and take the derivative in the denominator and find the derivative at the isolated singularity. So this formula is also for simple pole, but when the function is a rational function of this form, satisfying these two conditions. Okay, let me give an example for pole. So if suppose you have that fz is 1 upon 2 minus z, z square plus 4. You can see this has poles at z is equal to 2, means the denominator is 0 at z is equal to 2 and 2i minus 2i. So it has 3 poles. So what about the residue of f at the point 2? As I gave the formula, this is a simple pole. All three are simple poles. So this is limit z tending to 2, z minus 2 into fz. So this is going to be limit z tending to 2, z minus 2 divided by 2 minus z into z square plus 4. So this cancels and you have a minus sign. So this is, and you substitute the limit. So you have minus 1 because this is reverse of this. So this 4 plus 4 is 8. So minus 1 by 8 is the residue. Similarly, you can find out the residue at 2i also. This is limit z tending to 2i, z minus 2i into fz. So this is same as limit z tending to 2i, z minus 2i divided by, this is 2 minus z, this is z minus 2i and z plus 2i. When you factorize, z square plus 4. So when you substitute the limit, it is 1 upon 2 minus 2i, and this is 2 plus 2i, this is 4i. So basically this is 1 upon 8i, 1 minus I, and we never leave the complex number in the denominator. So this is basically 1 upon I square is minus 1, so this is plus 1, this is 1 minus I. So you multiply and divide by its conjugate. So this is 1 plus I divided by, see it is 1 minus I, A minus B, A plus B, which is 1 plus 1 minus iota square, which is 1 plus 1, 2. So this is 16. This is the residue at 2i. Similarly, you can find out residue at minus 2i also. But what about the second formula, which I gave? That if your function is of the form AA divided by BA, such that AA is not, sorry, AZ upon BZ, A is not equal to 0 and BA is equal to 0, then the residue of F at the point A, this is defined as AA divided by B dash A. Now, for example, if you consider Fz is equal to 1 upon Z4 plus 1. See, it has 4 simple poles, which are 4th roots of unity, because when you put this is equal to 0, you have z is equal to minus 1 raised to the power 1 by 4. Minus 1 can be written as cos pi plus iota sin pi raised to the power 1 by 4. Using De Moivre's theorem, what are the roots of this? This is 2k pi plus pi divided by 4 plus iota sine 2k pi plus pi divided by 4, where k varies from 0, 1, 2, 3. Okay, so you know, yesterday I told you that cos theta plus iota sine theta can be written as e iota theta. So in short form, I can say this is e iota 2k plus 1 into pi divided by 4, and k varies from 0 to 3. So these are the simple poles. So if we find using the previous method, it is quite tedious and lengthy. So we will adopt this. A, numerator is 1 and it does not vanish at any of these points. So A is not equal to 0. So we find out the derivative of the denominator. So what is this derivative? It is 4z cube. So we can write this as 4z cube. These are at the point, if I say this is zk. So these are at the point z is equal to zk. Okay. So let us multiply and divide by z so that it becomes z4, and z4 is equal to minus 1. So it is z upon 4z raised to the power 4 at the point z is equal to zk. Z4 is minus 1. So we have z upon 4 at z is equal to zk. And what is the value of zk? This is e iota 2k plus 1 pi divided by 4, 1 by 4. And you substitute k is equal to 0 to 3. So see, in 4 lines we are getting, otherwise you'll have to take each value for k is equal to 0, 1, 2, 3 and apply the previous. So this is a shortcut for finding the residue. So this is the residue at the point zk. Now next formula, if it is a pole of order k, so third formula, this is residue of poles of order k. So the formula for this is that 1 upon k minus 1 factorial, the derivative of k minus 1th order with respect to z of the function z minus a k fz, and this at the point of ith pole. Now, for example, that if we simplify, fz is equal to eiz divided by z raised to the power 4. So z raised to the power 4 is equal to 0 means that z is equal to 0 is a pole of order 4. So we substitute here k is equal to 4. So what about the residue at the point 0? It is 1 upon k minus 1, means 4 minus 1 is 3 factorial. Its third order derivative of what? This is z minus 0 raised to the power z4 into fz at the point z is equal to 0. So z4 into fz, if you multiply, this is only e iota z. So this is 1 upon this. Its third order derivative of e iota z at the point z is equal to 0. So if your function is, your f is e iota z or g is e iota z, so g dash is iota e iota z, g double dash is iota square, which is minus 1, g, its third derivative is minus iota e iota z. When you put here z is equal to 0, this is minus iota only. So this is 1 upon 3 factorial iota. And 3 factorial is 6. So this is the residue at z is equal to 0 using the formula for poles of order k. Now next formula for finding residue. This formula is for essential singularity. We use Laurent expansion for finding this. For example, that if you have that, find the residue of e raised to the power 1 by z. You know, it has essential singularity at z is equal to 0. So e raised to the power z, you know, 1 plus z square by 2 factorial, z cube by 3 factorial, and so on. So e1 by z, it is 1 plus 1 by z plus 1 by z square, 1 by 2 plus 1 by 6, 1 by z cube, and so on. Z is equal to 0 is the essential singularity. It means we want to find out the coefficient of 1 by z. So here you can see the coefficient of 1 by z is 1. So the residue of f at the point 0, it is 1. So these are various formulae for finding the residue. Now let us move to the applications. How do we find the integral, definite integration, and the contour integration using residue? First is the residue theorem. This is also known as Cauchy's residue theorem because Cauchy proved this theorem. So let C be a closed path within and on which F is analytic or holomorphic, except for M isolated singularities. These singularities can be whole, removable, or essential. It means we have this type of picture. This is a closed curve. We have here isolated singularity Z0, here Z1, Z2, and so on. And we have this is Zn. So these are singularities. The function is analytic everywhere except these points, in the neighborhood of these points, at these points. So then residue theorem says that if you want to integrate this function along the closed curve, this closed curve C, then this is nothing but 2 pi iota, the sum of the residues of the function f at these zj's, and how many isolated singularities are there? M. So 2 pi iota into sum of the residues at the singularities, isolated singularities. Now next is for finding along the using Laurent expansion. This is first formula for finding. The next formula is using Laurent expansion. Now, if we consider the Lorentz expansion, this is second formula for finding the integration. Consider Lorentz series expansion of f about a. This is fz is equal to sigma cn z minus a raised to the power n. N varies from minus infinity to infinity. You know, this is Laurent expansion. Where what is Cn? Where Cn is 1 upon 2 pi I integral along a path. This is f of xi divided by xi minus a raised to the power n plus 1 d xi. And we know the residue of f at the point A is nothing but the coefficient of 1 upon z minus a. And from here, what would be c minus 1? Means residue. So c minus 1, which is same as c minus 1, from here means you need to put n is equal to minus 1 here. So this is 1 upon 2 pi I integral. This becomes f zeta, f xi. This is minus 1 plus 1 is 0. So this is I minus a raised to the power 0. So we have this. So it means from here what we are getting from the Laurent expansion, that if you want to integrate f psi d psi, this is nothing but 2 pi iota and the residue of f at the point A. So this is another way of finding using Laurent extension. Now let's suppose you have a function fz which is given as 1 minus z upon 1 minus 2z whole square. And the question is find the integral of fz dz along a circle C, where C is the unit circle, means with center 0 and radius 1. So what is this? This is E iota theta, where theta lies between 0 and pi. So this is the expression in terms of complex number of a circle with radius 1, center at 0. So from here, as from the previous Laurent expansion, we have this is 2 pi I residue theorem, 2 pi I into sum of the residues. So from here, if you just see that z is equal to half is a pole of order 2. First thing is we can consider this function fz and we can make the partial fractions. When you make the partial fractions, you are getting this to be now first thing very important here, that these isolated singularities, they should lie inside this contour which we are taking, along which we are integrating. So z is equal to half because this is a circle with center 0 and radius 1. So half is somewhere here. So it lies inside. So what is the residue of f at the point half? This is nothing but the coefficient of 1 upon z minus half. You can see from here, from this expression, this is nothing but 1 by 4. Therefore, what about the integral of 1 minus z divided by 1 minus 2z whole square along this unit circle? This is nothing but 2 pi I into minus 1 by 4. So therefore, this is coming out to be minus pi iota by 2. So this is the integration. So you can see that the residue, calculation of residue has made the integrals along closed curves very simple. So I suppose you want to integrate along a unit circle sin z upon z raised to the power 6 dz. So you can see that z is equal to 0 is a pole of order 5. Why order 5? Because this is z6. Why order 5? Because if you have this sin z, its expansion, this is z minus z square, z cube by 3 factorial, z5 by 5 factorial, and so on. When you divide by z6, what happens? This is 1 upon z raised to the power 5 minus 1 upon 3 factorial, 1 upon z cube, plus 1 by 5 factorial, 1 upon z, and so on. So you can see that This is the largest negative term here. So it means this is a pole of order 5, not 6. Okay. Now, since this is a pole of order 5, and what would be the residue? You have in front of you the expansion. So this is nothing but the coefficient of 1 upon z minus 0. And you can see that the coefficient of 1 upon z is 1 upon 5 factorial. And what is the value of 1 upon 5 factorial? This is 1 by 120. So from here directly, you can find out the integration of z sine z upon z6. This is 2 pi I into 1 upon 120, which is pi I by 60. Now there is a twist here, that if suppose I say that using the same methodology, you find out the integration along the unit circle of this cos z. If you just see the cos z, if you expand, it is 1 minus z square by 2 factorial, z4 by 4 factorial, and so on. So cos z by z6, it is going to be 1 upon z6 minus 1 upon 2 factorial z4 plus 1 upon 4 factorial 1 upon z square, and so on. So z is equal to 0 is a pole of order 6 here. So what about the residue? Residue of f at the point 0. You can see that what about the coefficient of 1 upon z? There is no 1 upon z term here. All are even power term, 6, 4, 2, and then 0, z square, and so on. So it means the residue is 0. So what is the conclusion if residue is 0? So it means this is 2 pi I into 0. So this is equal to 0. So see, in case of sine, we are getting answer as pi I by 60. But in case of cos, this integration is equal to 0. So we have taken all unit circles, but if suppose, let C be a circle with center 0 and radius 3. And your function is dz upon, okay, this is 5z minus 2 upon z into z minus 1 along this circle. So you can see from here that z is equal to 0 and 1. These are poles of order 1 or simple poles. So this is nothing but 2 pi iota, the residue of f at the point 0 plus the residue of f at the point 1. Okay, if you make the partial fractions of it, so what about this 5z minus 2 divided by z into z minus 1? It is going to be 2 upon z plus 3 upon z minus 1. 2z plus 3z minus 2, yes. So when you integrate along the circle, this is going to be 2 pi I. And what about the residue? Residue is nothing but the coefficient of 1 upon z in case of this. So it is 2 only. And in the second case, and this 2 is also the coefficient. So this is 2 into, this is 3 is there. So 3 into 2 pi I into residue of f at the point 1 means the coefficient of 1 upon z minus 1. So this is 3. Sorry. So this is 3. So therefore it is 4 plus 6, it is 10 pi I. us move to the contour integration. If suppose you want to find out the definite integration from minus infinity to infinity of x square upon x square plus 1 into x square plus 4. See, this is x, means x is a real number because your z is, this is x plus iota y. X is the real part, means that we want to integrate this function from minus infinity to infinity. So for this, when we want to find out contour integration, we have to construct one contour, and this is the center 0. So for convenience, we take a contour with center 0, and this is the semicircle with large radius r, because r is tending to infinity. Okay, and we give this direction that we are starting from this point, moving along this direction, and then we are going through this. So what we do, that we divide this integration into two parts. One is along the straight line, another is with this. So we can convert, we replace x by z, because if we need to find only this, but we want to involve this contour also. So, and this portion, this is the part of the complex plane. So we write this to be z square upon z square plus 1 into z square plus 4 dz, and we want to integrate this along this contour, this total. This is denoted by this. So first part is along this line, and this is from minus r to r because radius is r, so minus r to r, and this is the part of the real. So that is why we are writing this x square upon x square plus 1 x square plus 4 plus along this semicircle of radius r. So this is z square upon z square plus 1 into z square plus 4 dz. So you can see that when we are integrating along this, we have taken x because it is along the real line, y is equal to 0. So z is left with only x. So that is why along this line, we are writing x only. So basically, when r tends to infinity, we want to find out the value of this. So it means we need to find out this and this. So let us first calculate this part. So let us take this as first part, this as second part, and this as third part. So to calculate the first, this is nothing but using the residue theorem. This is nothing but 2 pi I sigma sum of the residues of f at ai, where ai's are the residues, the isolated singularities, 1 to n, whatever singularities it have. So from this function, if you consider this to be fz, z square upon z square plus 1 into z square plus 4. The denominator vanishes at the point z is equal to plus minus iota and plus minus 2 iota. But if you just see the contour which we have taken, iota and 2 iota, these are inside this. This is iota, this is 2 iota, and minus iota is here, minus 2 iota is here. So they are not in the contour. So what is the conclusion? That only z is equal to iota and 2 iota are simple poles. So basically we need to find out the residues at these poles. So what about the residue of f at the point iota? The formula is limit z tending to iota, z minus iota into fz. So basically this is limit z tending to iota, this is z minus iota into z square upon z plus iota, z minus iota into z square plus 4. This cancels. When you substitute iota, iota square is minus 1. This is 2 iota, iota square is minus 1. So 4 minus 1 is 3. So into 3. So we are getting this to be minus 1 upon 6 iota. Similarly, the residue of f at the point 2 iota, this is limit z tending to 2 iota. This is z minus 2 iota of fz divided by z minus 2 iota z plus 2 iota into z square plus 1. This cancels. So, sorry, fz, this is z square. So if you substitute 2 iota square is minus 4 divided by 2 iota plus 2 iota is 4 iota. Z square is minus 4 plus 1 is minus 3. So therefore it is 1 by 3 iota. So therefore the integral of fz, which is z square upon z square plus 1 into z square plus 4, which is the first part, dz along the closed contour, this is equal to 2 pi iota into sum of the residues, which is minus 6 iota plus 1 upon 3 iota. So basically this is coming out to be iota cancels, 2 3s are, so it is 1 by pi by 3 minus pi by 3 plus 2 pi by 3. So this is coming out to be pi by 3. So first part is pi by 3. Now we had this closed contour. This is minus r and r. So obviously this is semicircle. So what is the this is SR. So what is the equation of SR? This is equal to RE iota theta, and theta lies between 0 and pi because this is the upper semicircle. So let us calculate the second part. First part is coming out to be pi by 3. For the second part is z square upon z square plus 1 into z square plus 4 dz, and this is along the semicircle. The equation of the semicircle, this is the set of all those z such that z is equal to r e iota theta, and theta lies between 0 and pi. So when you substitute z is equal to r e iota theta, so dz is nothing but iota r e iota theta d theta. Let us substitute here. This is, and we take modulus also. So this is minus 0 to pi because the limit is 0. Z square means r square e2 iota theta d theta into dz is this. So it is into iota r e iota theta d theta divided by z square. It is r square e iota e2 iota theta plus 1, and this is r square e2 iota theta plus 4. So further we can write this to be, this is r cube, mod iota is 1, so this is r cube. When you take this modulus inside, this is less than or equal to 0 to pi e 3 iota theta mod d theta divided by mod r square e2 iota theta plus 1 and r square e2 iota theta plus 4. And you know that modulus of x plus y, this is greater than or equal to mod x minus mod y. When you take its reciprocal, this is less than or equal to mod x minus mod y. So from here, this is r square minus 1 and this is r square minus 4. So you can write this to be r cube. This is divided by r square minus 1, r square minus 4, because this is independent of theta, so we can write. So we have, this is mod theta, you know, this is the mod. When you have mod theta, this is nothing but the length. So length of this semicircle, what about the length of this 0 to pi? This is circumference hota na 2 pi r, so this is pi r only. Sorry, when you integrate, this is pi only. Integrate 0 to pi d theta, so this is pi only. You can see When r tends to infinity, the power in the denominator is r4. So this tends to 0 as r tends to infinity. So let us combine all the things and we take the limit. So we had first part, second part, plus third part. Second part was, first part was coming out to be pi by 3. This was pi by 3. The second part was minus r to r x square upon x square plus 1 into x square plus 4 dx. The third part was along the semicircle z square dz upon z square plus 1 into z square plus 4. You know, this part is tending to 0 when r tends to infinity. Then the third part tends to 0. So we have pi by 3. This is minus infinity to infinity when r tends to infinity, x square dx upon x square plus 1 into x square plus 4. So you can see that using residue, we have calculated this integral because this part is 0. Now, if some trigonometric function is given, because we have several types of problem here, we have 5 types of problem in contour integration. I don't know how much time will I have, whether I would be able to complete it not, but I'm trying. This is the first type where the function fz, this is of the form pz upon qz, where p and q are polynomials. So this was numerator polynomial, denominator polynomial. So this is a rational function of polynomials. So this was the first type of integration which can be solved using residue. The second type is when we have function in terms of trigonometric function. Trigonometric. So if suppose you have this, you calculate 0 to 2 pi, 1 upon 2 plus cos theta d theta. So here the numerator is a polynomial. The second type of is that we have polynomial divided by trigonometric function. So in this case, you know that this is 0 to 2 pi. So it is understood that we want to integrate this along a circle with center 0 and radius 1. So therefore, we have z is equal to e iota theta, and this is nothing but cos theta plus iota sine theta. When you take 1 upon z, so this is nothing but cos theta minus iota sine theta. So from here, if you just add the two, what you are getting, z plus 1 by z, this is 2 cos theta. So we have this cos theta is nothing but 1 by 2 z plus 1 by z. The same technique can be adopted if your function is of the form that you integrate 0 to 2 pi d theta upon 2 plus sine theta. Because here when you subtract, you are getting sine theta as 1 by 2 iota z plus 1 by z, when z minus 1 by z. So you can substitute. Similar type of problem parallelly can be solved. Now, we know the value of cos z because we want to convert this in terms of z. So therefore, this integration, if I say this is I, so I can be written as integral along circle C, which is a unit circle. This is 1 upon 2 plus, substitute the value of cos theta. This is 2 half plus 1 by z d theta from here. See, your z is e iota theta. So dz is iota e iota theta d theta. So from here, your d theta is nothing but dz upon iota z. So therefore, this d theta is dz upon iota z. So we can further write, if you just take the LCM and simplify, you are getting this to be, this is 2. So it will be in the numerator. So you have 2 upon iota integral 1 upon, this is z in the denominator. When you take LCM, this z cancels with this. So you have z square plus 4z plus 1. After simplification, you will get this. This is dz. So again, see here, This is already a contour, a circle. So no need to take any other contour in this case. This is directly a circle. If it is given minus infinity to infinity, then obviously we need to construct a contour along which we want to integrate. Okay. So this is along C. Now what about the poles of this? Poles of this would be where this is equal to 0. So if we just simplify, this is minus 4 plus minus under root 16 minus 4 AC minus 4 divided by 2. Minus 4 plus minus 16 minus 4 is 12. 12 can be written as 4 into 2. So this is 2 root 3 divided by 2. So therefore it is minus 2 plus minus root 3. So these are the two poles. Now what about the circle? This is a unit circle. If you take minus, so minus means minus 2 minus root 3, it would exceed, it would be outside of this, somewhere here. So obviously this negative value we won't take, but if you take minus 2 plus root 3, it is going to be, because root 3 is 1.718, so this is going to be inside somewhere here. So we have, it has only one pole. So you can say that only z is equal to minus 2 plus root 3 lies inside C. So we need to find out its residue. So residue of this would be, so let me take Z1 as, for simplicity, this, and Z2 as minus 2 plus root 3. So we want to find out the pole at the point Z2. Z2. So residue of F at the point Z2, this is nothing but limit Z tending to Z2, Z minus Z2 into Fz. And Fz is what? 1 upon Z minus Z1 into Z minus Z2. This cancels. So basically Z minus Z tending to Z2. So this is nothing but 1 upon Z2 minus Z1. See, this is Z1, this is Z2 when you take Z2 minus Z1. So 2 cancels and you will have 2 root 3. So this is 1 upon 2 root 3. This is the residue. So therefore, this integration, we have 2 upon iota outside. This is 2 upon iota. So by using the residue theorem, this is equal to, your I is equal to, first is 2 pi I, 2 by iota is outside, and into the residue. Residue of this was coming out to be 1 upon 2 root 3. So therefore, it is coming out to be 2 pi by root 3. So see how simple is this? Now next is a problem which involves the third type. Third type of is that we have exponential multiplied with some trigonometric function. This is third type of contour integration, which can be solved using residue. So here, if suppose the question is, find the integral 0 to 2 pi e minus cos theta into cos of theta plus sine theta d theta. Parallelly, the same type of equation can be solved if suppose I write this to be I1 and I2, the parallel integration function can be 0 to 2 pi e minus cos theta sine of theta plus sine theta d theta. So both of can be solved simultaneously. Again, we have, because this is 0 to 2 pi, so this is understood that we want to integrate this along a circle, unit circle. So this is e iota theta d theta. So what about cos theta? This is e raised to the power minus 1 by z if you consider. This is e raised to the power minus e minus iota theta. which is same as e raised to the power minus cos theta plus iota sine theta. Okay. So basically, the real part of e raised to the power minus 1 by z is e raised to the power minus cos theta. So therefore, this integration can be written as this one I1. This is e raised to the power minus 1 by z dz. If I just calculate, this is equal to e minus 1 by z, real part. It is e raised to the power minus cos theta. And this is e iota theta plus, because dz is what? E iota theta d theta, right? And its second part is this. E minus 1 by z, it is along C. E minus cos theta, E iota sine theta. This is E minus 1 by z. And dz is iota, E iota theta, d theta. This is from 0 to 2 pi. So this can be written as 0 to 2 pi E minus cos theta, E iota theta plus sine theta, d theta. So this cos is the real part of this and sine is the imaginary part of this. So both answers we can get. If so, it means this can be written as iota I1 plus iota times I2. If you just expand, this is nothing but cos of theta plus sine theta plus iota times sine of theta plus sine theta. So that is why we can write like this. So we can calculate this using the residue theorem. So this is nothing but 2 pi iota residue at the point z is equal to 0. And e minus 1 by z, this is essential singularity. And I just told you that when you expand ez, this is 1 plus z square by 2 factorial, z cube by 3 factorial, and so on. So therefore, e raised to the power minus 1 by z, it is nothing but 1 minus 1 by z plus 1 by 2 factorial 1 by z square minus 1 by 3 factorial 1 by z cube, and so on. So what is the coefficient of 1 upon z? This is from here minus 1. So therefore, this is minus 2 pi iota. So if you substitute here in I1 and I2, what we are getting. So we are getting from 1 that minus 2 pi iota, this is equal to iota I1 minus I2. But for this, we want to find out this is I1. So I1 is what? That this is you just compare the imaginary parts on both the sides. So from here, what is the value of I1? This is minus 2 pi. And what is the value of I2? It is equal to 0. So this integration is equal to 0 and this integration is equal to minus 2 pi. So that is why I gave both the integrations parallel. Now next is the third type of integration. A fourth type. The fourth type of integration, this is from 0 to infinity cos x upon 1 plus x square dx. So this fourth type, this is nothing but that we have trigonometric function divided by a polynomial. This is given from 0 to infinity. So obviously we need to construct a contour. Again, we consider the contour from minus infinity to infinity, means minus r to r. This is 0 and this is the direction. So first thing is that we want to construct this cos x. X is there. So we can consider cos z. This is cos z upon 1 plus z square. The corresponding function in the complex plane. Sorry, this is e iota z cos x ln. So this function is e iota z dz divided by 1 plus z square. Because when you take e iota x, this is nothing but cos x plus iota sin x, and this is the real part. That is why we are considering this. So this first is, this is along the contour. So we write this is equal to along the real line, which is minus infinity to infinity. This is what e iota x divided by 1 plus x square, because this is along the real line, plus the semicircle. This would be e iota z dz upon 1 plus z square. So this part, this is solved by finding the residue. So this is first part, this is second part, and this is third part. So we take first part. This is e iota z dz upon 1 plus z square along this contour. So this is nothing but, by residue theorem, 2 pi iota residue. And what about the residues? Residues are 1 plus z square is equal to 0. So z is equal to plus minus iota. So plus iota is here, but minus iota is here. Only z is equal to iota. It lies inside. So z is equal to iota is a simple pole inside contour. So we have to find out its residue. So what about the residue of f at the point iota? This is limit z tending to iota. Z minus iota into fz. So this is nothing but fz is your e iota z divided by z minus iota z plus iota. So this cancels. When you put I, e iota square is minus 1 divided by 2 iota. So this is 1 upon 2 iota e. This is the residue. Therefore, when you substitute here, so we are getting what? E iota z along this contour. This is 2 pi I into 1 upon 2 iota e. So which is same as pi by e. So this integration, this first part is nothing but pi by e. Let us calculate the third part. Third part is along the contour semicircle. This is e iota z divided by z square plus 1 dz. So this semicircle, again, this is the set of all those z's such that z is equal to r e iota theta, and theta lies between 0 and pi. Semicircle. So when you find out dz of this is r iota e iota theta d theta. So this is equal to, when we take mod also, mod integral 0 to pi e iota r e iota theta into iota e iota theta d theta divided by e r square, sorry, this is r square e 2 iota theta plus 1 mod. So this is less than or equal to, so this iota theta, anything, and you can calculate this also. You have e iota theta, this is cos theta plus iota sine theta. When you take r, so this is r cos theta, r this. When you take exponential, this is e iota r e iota theta. This would be cos of r cos theta plus iota r sine theta plus iota sine r cos theta plus iota r sine theta. So basically this is going to be, when you take modulus, it is going to be 1. So this is 0 to pi less than or equal to d theta, because mod of e theta is 1, iota is 1. This becomes r square minus 1 mod of r square minus 1, and this tends to 0 as r tends to infinity. So the third part is tending to infinity. Now see, the first part was coming out to be pi by e, and this was minus infinity to infinity, e iota x divided by x square plus 1 dx, and plus 0 when you take r tends to infinity. But we wanted to find out 0 to infinity. So 0 to infinity is nothing but half of minus infinity to infinity. So it means this is nothing but 2 times 0 to infinity e iota x, which is same as cos x plus iota sin x divided by x square plus 1 dx. But we want to find out only cos part, this part. So we have to equate the real part on the opposite side. There is no imaginary part. So what we have, that 0 to infinity cos x upon 1 plus x squared dx. This is nothing but pi by 2e. We bring this 2 on this side. So this is pi by 2e. So this is the next part. So Pravinji, time is over. I think let me stop because 2-3 more methods are left. So
Yes, ma'am.
thank you very much for the patient hearing.
Is there any query? So thank you so much, ma'am, for giving such a wonderful talk on calculus of residue. I hope everyone get benefited by this lecture. I again express my sincere thanks to Dr. Anuradha ma'am for sparing her valuable time to enlighten all of us. So thank you so much, ma'am.
Thank you, Shashiji. Thank you so much.
Thank you.
I'm leaving the meeting.
Yes. नमस्ते सर. सर, हाँ जी, सर, can I start, sir?
Yeah, sure.
Okay, sir. I, Dr. Meenu Chawla, on behalf of the Department of Mathematics, J.C. Bose University of Science and Technology, YMCA, Faridabad, I welcome you, sir. It's my pleasure to welcome the eminent speaker, Professor R.C. Mittal, sir. Sir, it is our pleasure to hear you.
Thank you, madam.
Today's topic is conformal mapping. Sir, you can start.
Okay. So thank you, madam, for your nice words. So let me start directly. So can you see my PPT, please? Hello?
Yes, sir. Sir, you are audible, sir.
Audible and my PPT visible?
No, sir, it is not visible.
Okay. Let's go back. Present. इसको करें. Is it visible now? Hello?
Yes, sir. Yes, sir. Yes, sir.
Just a minute, please. इसको बंद करो यार. So I hope my PPT is visible now. Friends, today I will talk about conformal mapping, which will have introduction to conformal mapping, then examples, then bilinear transformations, and then the examples of the bilinear transformation. Now, before I take formal definition of conformal mapping, let me say a few words about the importance of the conformal mapping. I hope most of you are from engineering background, and you are taught number of transformation like Fourier transformation, Laplace transformation, and same way, conformal mapping is also one of the transformation. Now, what we do in the transformation is that we are given a problem and we transform the problem into a suitable, convenient domain. And then we do the analysis of the problem in the convenient domain to conclude important information about the problem. And then those information go back to the original domain and see whether they are applicable there or not. That is what a conformal mapping does. I have been given a problem in a domain which is not so convenient to me. It could be some polygonal or some domain which is very ill behaving in the sense that it is a boundary, is a fractal, something like that. What we do is that let's say our domain is simply connected. Then what we do is that we take conformal mapping and transform the domain into a suitable domain, which could be a circle or could be a left half plane or could be a right half plane. And then I do my analysis there. I solve the problem there. And since I know the problem in the circle or the half plane, the corresponding solution, I go back to the original domain by the inverse of the transformation, and then the solution can be obtained at that point. So that's why conformal mapping is very important, what you call area. So I consider now what is the definition of the conformal mapping. So suppose I am given two curves C1 and C2 in Z plane, and they intersect at the point what you call so they intersect at the point Z0, and Z1 and Z2 are 2 points. Z1 is on the curve C1 and Z2 is on the curve C2. The distance between Z0 and Z1 is same as distance between Z0 and Z2. That is, the distance Z1 minus Z0 is R, and distance Z2 minus Z0 is also Z. And that's why I can write Z1 as Z0 plus R EI alpha or some alpha, because it will be having some value of alpha angle. And same way, I can write Z2 as Z0 plus R EI beta. So that way, two coordinates or 2 points Z1 and Z2 can be represented. Now, yeah. So let W equal to FZ be my transformation, such that under the transformation, the curve C1 goes to C1 prime and the curve C2 goes to C2 prime. So I can write now that my new point W1 in the C1 prime is FZ1, and my W2 point in the C2 prime is fz2. Since let's say that these 2 points W1 and W2, they are at the distance rho from the W naught. Z naught goes to W naught. Then I can write W1 is equal to W naught plus rho EI theta. The angle is the theta from the pole. And same way I can write W2. This is not W1. This is the W2, which is equal to W naught plus rho EI phi. And then I find derivative of my function at fz, which I consider as a conformal mapping. So what is the property of conformal? I am coming to that. So I take its derivative at z naught, which is nothing but limit as z1 tends to z naught, w1 minus w naught, that is f of z1 minus f of z naught upon z1 minus z naught. Now w1 minus w naught is already rho ei theta, and z1 minus z naught is already r ei alpha. So I can write this ratio as capital R, when R rho goes to as a limit, rho goes to capital R as R tends to 0. So that what the value of the first, if I take one curve C1 from along that, I get this value. Now same thing.
Sir, excuse me, sir. Sorry to interrupt you.
Yeah,
Sir, your slides are not moving.
slides are, you are not getting second slide, please. Are
No,
you seeing?
only first slide is visible for formal mapping.
Okay, please, I go back.
Yes, sir, it is visible now.
Second slide visible now?
Yes, sir.
Okay, I go to, this is okay now, please?
Yes, sir. Yes, sir, it is okay now.
I move that. Is it ready to see?
Yes,
Hello?
so visible.
Visible now?
Yes, sir.
Okay, okay. So let me go back. As I said in the beginning, I have two curves, C1 and C2. They intersect at Z0. There is a point Z1 on C1 at a distance R. So the distance between Z1 and Z0 is what you call small r. And similarly, Z2 is on C2, such that Z2 minus Z0 is also distance R. So I can write Z1 as Z0 plus R EI alpha. That is because the Z1 minus Z0 modulus is R, and since I want to represent Z1, so it takes the value alpha with the x-axis. So I have Z1 equal to Z0 plus R EI alpha. Similarly, my Z2 point will be Z0 plus R EI beta. So these are the 2 points of the curve C1 and C2 respectively. Now, I take my transformation as W equal to Fz. So under the transformation, my curve C1 goes to C1 prime, my curve C2 goes to C2 prime. And I choose to point W1, which is nothing on the C1 prime. First point W1 on the C1 prime, which is nothing but image of Z1 under F. And similarly, there is a second point W2 on C2 prime, which is image of Z2, that is W2 equal to FZ2. Now, since those 2 points are equidistant from Z0, one of the property of the control map is that it preserves the distance. That is, the distance of W1 minus W0 modulus is same as W2 minus W0 modulus, I say that distance as rho and represent by equation 1. And that's why I can write my point W1 as W0 plus rho EI theta. That is, it makes an angle theta with the x-axis. Then my second point W1 is equal to W0 plus rho EI phi. Now I try to find its derivative of the function fz at z0. So when I try to find the derivative of fz at z equal to z0, there are two curves between C1 and C2, and the both should have the same value because as you've been told or you have been taught that if derivative it does exist, then it is not depending on the curve. So when I take along C1, I get limit at Z1 tends to Z0, W1 minus W0 upon Z1 minus Z0. My W1 is at Z1, my W0 is at Z0, and so it is giving the value of F prime at Z equal to Z0, and which is coming out to be, I have this ratio because W1 minus W0 I have already found as rho EI theta, and Z1 minus Z0 I have already found that R EI alpha, and when I take this, I get my value as R tends to 0, rho tends to R, capital R EI theta minus alpha. So this is my value of f prime z0 when I go along C1. Similarly, when I go along C2, take the limit as z2 tends to z0. This is z2 because I'm coming to second point. So this is z2, please. This is wrong. So this is z2, and then what you have is limit as w2 minus w0 upon z2 minus z0, which is nothing but taking the limit I get as just a minute, please. Okay, I resolve the problem, please. I want to write something, that's why. Okay, no problem, please. Let me go ahead. No problem. अब मेरे को तो देख के बताओ क्या करना है. So okay. So what I get from this is that both limits should be the same, and hence the value of f prime z0, which I get as capital R EI theta minus alpha, so equal to capital R e raised to power I phi minus beta, and ultimately what I'm getting is that theta minus alpha is equal to phi minus beta. And since theta minus alpha is equal to phi minus beta, so what I get out of it is that theta minus phi is equal to alpha minus beta, and meaning that f prime z should not be 0. That is, theta is not equal to phi, alpha is not equal to beta because they are two distinct points, and in that case, the angle between two curves are retained. So one of the beauty with the control mapping is that it preserves the angle as well as the distance. So that is what it is. That is, a conformal map is the map which take a curve, and if you take angles, it will preserve the angle at that point. So, and the value of f prime z at that point should not be zero. Should not be zero. Now, if I take fz equal to u plus iv, which is every complex function is having, then the angle of rotation by fz will be given by theta, which is nothing but tan theta equal to v over u. The second point is that under w equal to fz, the magnification at z equal to z naught is nothing but the absolute value of f prime z naught. So what it does is that it give you the value of f prime, the magnitude will be changing with the f prime z naught. Now, क्या चीज है? Okay, now let us take some example so that we can understand. Now, first, please try to understand me. There are some technical problems, but if I let me again. Okay, no problem. I will just, please listen to me now. So, let's take examples. Find the image of the triangle with vertices at 1, 1 plus I, and 1 minus I under the map w equal to 3z plus 4 minus 2I. Now, before I take this transformation, please try to see that w equal to az. If I take simple linear transformation, w equal to az, what it will do? It will magnify if a is real, it will magnify the z point by value a, where a is positive number. Or the modulus of a will magnify the magnitude of z by that value. So it is scaling. And if a is a complex number, then I can write this as ER into EI alpha. Then the magnitude of z will be magnified by R, and the z will be rotated by angle theta, because this is R EI alpha. So the point z will be rotated by EI angle alpha. On the other hand, if I write AZ plus B, then it will be doing magnification as well as rotation plus translation, because I write AZ plus B, that is after doing magnification and rotation, the point will be going to a new point 4 minus 2I in this case, or B. So let's see that I have a triangle whose vertices are 0, 1, 1, 1, and 1 minus 1. These are the 3 points: 0, 1, 1, 1, and 1 minus 1. Now, if I take my transformation, then my transformation says that my W goes to 3x plus 4, because Z is x plus iy. So when Z is x plus iy, my W is, the real part of W is 3x plus 4, and the imaginary part of W is 3y minus 2. And small w goes to 3x plus 4 plus I times 3y minus 2. And my points vertices are 0, 1. So 0, 1 goes to, according to it, 4, 1. My 1, 1 goes to sorry, 0, 1 goes to 4, 1, 1, 1 goes to 7, 1, and 1 minus 1 goes to 7 minus 5. And so my triangle having the vertices at 0, 1, 1, 1, and 1 minus 1 becomes a new triangle whose vertices are 4, 1, 7, 1, 7 minus 5. Friends, the point which I want to tell you is that uh, the size of new triangle will be larger than the given triangle because I am multiplying by 3. Or you can understand this in this way, that area of the new triangle will be nothing but half a square, or it will be multiplied by a square or multiplied by 9. So this is the area will be multiplied by magnification factor square, and at the same time it will be so it will be magnified, yeah. It will be magnified uh, by 9 because my a is 3. So this is the first example. Let me take second example. Let's consider the transformation W equal to 1 over Z, and obviously Z should not be 0 because otherwise W goes to infinity. This is not a big deal, but anyway, Z is not 0. Now, this transformation, by multiplying by Z bar at denominator and numerator, I can write W equal to Z bar upon R square. Z bar upon R square. Therefore, what is that? Let's see that, because Z bar is nothing but reflection about x-axis. I hope you understand. If my point is Z is x plus iy, and if I take Z bar, then W equal to Fz equal to Z bar is nothing but x becomes minus, y becomes minus y. So it becomes x minus iy. So what it does is that it reflects the point Z around x-axis and magnify it by 1 over R square. So that's what this transformation generally will be doing. Now, if I take a circle, so I take a general circle, which is given by the equation which is you know from the high school, that a into x square plus y square plus 2gx plus 2fy plus c equal to 0. It represents the circle whose what you call center is minus g by a and minus f by a, and whose radius I can find by g square plus f square minus under root of c upon a. Anyway, I can find the radius and what you call center of this circle. So I take general circle, and my transformation is w equal to 1 by z. So w is equal to u plus iy, and this becomes as per written here, that my z bar is nothing but x upon x square plus y square minus I times y upon x square plus y square. So as per this, r square is x square plus y square. So x upon x square plus y square minus I times y upon x square plus y square. Now, since w equal to 1 by z, so z is 1 upon w. Now, so since z is 1 upon w, so same kind of analysis I can do, and I find that my x is nothing but u upon u square plus v square, and y is nothing but minus v upon u square upon v square. The same way was multiply by w bar bottom and numerator, and you get the same thing. But when I substitute this given equation 5, then what I get is c times u, because u square plus v square was in the denominator. So the equation becomes now, because this was the denominator, So it becomes now C times U square plus V square plus 2GU minus 2FV plus A equal to 0. And so what we find is that the circle is transformed to circle again, because this is equation 6 is a equation of a circle. So my circle is transformed to a circle again. However, if I take particular value of what you call my constant, then I will see that what is happening. So if I take A equal to 0, then equation 5 represents a line, because if I take A equal to 0, then this x square plus y square terms will not be there. So this term will not be here. So you understand 2gx plus 2fy plus c is nothing but your line. So if a equal to 0, 5 represents a line, however, 6 represents a circle. So your line is going to a circle which is passing through the origin, because there is no constant a 0. On the other hand, if c is 0, in that case, 5 represents a circle passing through the origin, and it is translated or transformed to what you call your circle to a line, because when I put c equal to 0 here, c equal to 0 here, then this will be going off, and my equation of line, equation of the 6 becomes 2gu minus 2fv plus a equal to 0. And so it becomes a line, circle becomes a line. And if I put a equal to 0 and c equal to 0, in that case, this becomes gu minus fv, which is nothing but a line passing through the origin. So that's what it is. Let me take now another example, which is what you call image of a hyperbola x square, rectangular hyperbola rather, x square minus y square is equal to 1 under w equal to 1 by z. So my same transformation. Now I am taking my curve h, x square minus y square equal to 1. Now, if I write x is equal to r cosine theta and y equal to r sine theta, which is the coordinate system in the polar, then my hyperbola become r square cos square theta minus r square sine square theta. And since cos square theta minus sine square theta is equal to cos 2 theta, I get equation of the what you call hyperbola h, r square cos 2 theta equal to 1. So if I take w equal to r phi is the polar representation of w, then this becomes r ei phi equal to 1 upon r e to the power minus I theta. And then I get from here that my r is capital R is 1 upon r, and my phi is what you call minus theta. And so if I put the equation, then small r is nothing but 1 upon capital R. I put here in the equation, this becomes 1 upon r square, capital R square, cos 2 phi equal to 1, or r square is equal to cos 2 phi, which is nothing but equation of the Lemniscate. If you are taught is okay, otherwise this is something like infinity this curve, something like infinity this curve. So this will give you a Lemniscate, that is my hyperbola is transformed into two loops like thing. And please understand, my hyperbola is also having two parts. My hyperbola is something like this. I hope you understand me. This is rectangular hyperbola, So my hyperbola is something like this. So this is translated or mapped into the Levin scale. Let me come to the another example. Find the image of the circle mod z minus 1 equal to 1. That is, I have a circle whose center is 1, 0, and whose radius is 1. Under the transformation w equal to z square. W equal to z square. Now here circle can be written as we have written earlier, because mod z minus 1 equal to 1, meaning that z equal to 1 plus ei theta. So this is my z in the polar form, and my transformation is w equal to z square. So w becomes 1 plus ei theta whole square. Now if I take ei theta out, I mean to say ei theta by 2 out, and instead of that become ei theta, then this become here become ei theta 2, and here become 1 become plus e minus I theta 2, because I am taking ei theta by 2 out and is square here. So this become ei theta. This become ei theta, and the rest of the thing here become ei theta by 2 plus e minus I theta by 2 whole square. And as you understand, this is nothing but what you call this is 4 times, because upon 2 is cosine theta, so it becomes 4 times cos square theta by 2 into ei theta. So that is what my w will be. And if I take real part and thing, and so my capital R will be 4 cos square theta by 2 in the polar form, and my phi will be nothing but theta. And hence, this circle now becomes, because I put in the equation, and this circle becomes that my R is 4 cosine square theta by 2. My phi is theta, and so in the equation, if I write, then the equation which I am getting is R equal to 2 times 1 plus cosine phi. And because, as you understand me, my phi is theta, so this becomes 4 cosine square phi. So my capital R, when I put phi equal to theta equal to phi, so this becomes 4 cosine square theta by 2. And you know 2 cosine square theta by 2, pi by 2 is equal to 1 plus cosine phi. So this becomes equation of form R equal to 2 into 1 plus cosine phi. And this curve is known as cardioid, which is nothing but cardioid, it means your heart. This curve becomes something like this. So this is what your curve called cardioid is. That is, cardioid means the shape of heart, or the art of the science of cardioid heart is known as cardiology. So this curve is cardio. Then let me come to my another part, which is nothing but bilinear transformation. So when I want to discuss bilinear transformation is also one of the conformal map, and which is very useful. When I take some example, you will understand just now. What bilinear transformation is? A transformation of the form W equal to AZ plus B upon CZ plus D is known as a bilinear transformation. And by bilinear transformation, I can always map what you call a simply connected domain to another simply connected domain. And that's why bilinear transformation are very important, because there is a famous Riemann mapping theorem. And what Riemann mapping theorem says is that every simply connected domain can be conformably mapped into another simply connected domain, or precisely it says that every simply connected domain can be transferred to a circle, or I can say to a unit circle, because from circle radius divided by the radius of the circle, it becomes unit circle. So that's what it is. That is, every simply connected domain can be transformed to a circle, which I'm going to use to give an idea. What I mean to say is that my transformation W equal to AZ plus B, this will be conformal if AD minus BC is not equal to 0. So if AD minus BC, that is their cross, this is, if I write a matrix A, B, C, D, then the determinant of matrix A, B, C, D should not be 0. Or AD minus BC should not be equal to 0. Now, if I see my transformation, I can divide by C, because there are 4 constants, but let's understand this also. So when I divide by C, numerator and denominator, what I get is A by C Z plus B by C upon Z plus D by C, where I assume that my C is not equal to 0. And then I write A by Z, I write A by Z equal to alpha, and what do you call your B by C, sorry, A by C equal to alpha, B by C equal to beta, and D by C equal to lambda. Then this same transformation becomes A alpha Z plus beta upon Z plus lambda. What is the meaning of this? The meaning of this is that from 4 constants, now I have only 3 constants. What are those 3 constants? Alpha, beta, gamma. That is, to determine a bilinear transformation, you need at least 3 information. You need 3 points, which is back into what we call points, namely W1, W2, and W3. That is, if I know the information that there are 3 points Z1, Z2, Z3, all are different, such that Z1 goes to W1, Z2 goes to W2, and Z3 goes to W3, then it is sufficient, this information is sufficient to me to find my bilinear transformation. So that is the utility. Out of 4, 1 constant can be done away with. Now, if I take some example, so my first example is that I take bilinear, I want to find a bilinear transformation where my point Z1 goes to 1. So my Z1 goes to 1, my Z2 goes to 0, and my Z3 goes to infinity. That is, I want to find W equal to AZ plus B upon CZ plus D, such that my Z1 point goes to 1, any point Z1, which I will, so you will see that. So Z1 goes to 1, Z2 is different than Z1, which goes to 0, and Z3 is different than Z1 and Z2, which goes to infinity. Now, what I see is that Z2 goes to 0, therefore, I should have something like W equal to a constant times Z minus Z2, because Z2 goes to 0. So my simple linear transformation will be W equal to A into Z minus Z2. So the moment I put Z equal to Z2, W becomes 0. Now similarly, my Z3 goes to infinity. So my simple algebra says that it should be in the denominator. So I have W equal to 1 upon B times Z minus Z3. So the moment I put Z equal to Z3, this goes to infinity. And so my W will be something like a constant capital A times Z minus Z2 upon Z minus Z3 because it gives me that my Z2 goes to 0 and my Z3 goes to infinity, and I need only to determine A. So I put Z1 which goes to 1. So the moment I put W equal to 1 is equal to A times Z1 minus Z2 upon Z minus Z3, and my capital A is obtained. So this transformation can be written as Z minus Z2 upon Z1 minus Z3. This is my what we call numerator divided by Z minus Z3, and my numerator in the A comes to here, which becomes Z minus Z2. So the transformation can easily be obtained because I am given three quantity. The quantity Z1 minus Z2 upon Z1 minus Z3 is known as cross ratio. It's known as cross ratio. So this is known as cross ratio. Now let me take another transformation, which is find the bilinear transformation which maps minus I to minus 1, 0 to I, and I to 1. So I need to find a transformation where minus I goes to minus 1, 0 goes to I, and I goes to 1. So these are the reflectors. You can see this is the reflection. This part and this part, they are reflections of each other. So let's say my WH AZ plus B upon CZ plus B. Then, since my 0 goes to I put Z equal to 0. So what I get is I equal to B by D, or B equal to ID, because Z equal to 0 gives me B by D. Now similarly, my I goes to 1. When I goes to 1, I have W equal to 1 equal to Z is I, so I get AI, B is become now ID because I find here that B is ID. So when B become ID, this become AI plus DI upon CI plus D because Z is I. And this I is the numerator, and I here can be cancelled out, and I can find this as A plus D upon C minus ID. Now, the reflection of this, as you understand, I will be having, or Z bar of this, I will be having this minus I. Minus I goes to minus 1. The meaning is that minus 1 is equal to minus AI plus DI upon minus CI plus D, because I put Z equal to minus I. So this becomes, when I simplify, cancelling out I, then I get this as D minus A upon minus C minus DI, or simply A minus D upon C plus DI. So I get two equations, 10 and 11, they are quite similar. Only thing is that there is a plus sign, there is a minus sign. So minus become plus, plus become minus. That's what is happening. So I equate them, that is from the transformation, because they are equal to given quantity. So when I 1 and minus 1, so use them. What I get is that when I do the simplification, I get C minus ID equal to A plus D, and minus C minus DI equal to A minus D. And from this, very simply, I get A minus A equal to minus ID and C equal to D. Because solving this, you very easily, you add and you get the one quantity, and subtract, you get another quantity. And my transformation now become W equal to I times 1 minus Z, 1 plus Z. Now, I take another transformation, and please pay attention to this transformation because this is important. So I have the transformation W equal to I upon Z minus I. So what I'm having is that here Z equal to I times 1 upon W because the moment I write W equal to I upon Z minus I, then I multiply both sides by Z minus I get WZ minus IW is equal to WI. And ultimately, I get Z equal to what you call I times 1 plus W upon W. So this is, if I have Z, I can know my W. And when I have W, I can know my Z. Now, suppose I take my unit circle, which I was talking about. To you. So, if I take my unit circle center at 0, unit circle is the center at 0 always, then I take the mod of map. What I get is that mod of W become, because I take mod of Z here, mod of here, I get from here that mod Z equal to 1. Since mod Z equal to 1, so I get mod of W is equal to mod of 1 plus W. And then what I get is U square plus V square is equal to 1 plus U whole square plus V square. And then because of mod Z equal to 1 plus mod 1 plus Z, I get this equation. And then when I simplify it, what I get is 2U plus 1 equal to 0. What is the meaning? The meaning is that my circle mod Z equal to 1 or my unit circle goes to the line in the UV plane 2U plus 1 equal to 0 or the line U equal to minus half. However, if I take the unit disk, the interior of unit circle, interior of unit circle, that's called unit disk, then it will goes to left half plane 1 plus 2U equal to 0. 1 plus 2U equal to 0. And that's what it is. That is, my circle can be transformed to left half plane. Please try to understand me. If I want to go through origin, I have to just translate the map by plus half. So minus half become plus half. Translated by plus half, it goes to 0. So what I mean to say is, a unit circle can be transferred to left half plane, or on the other hand, a left half plane can be transformed to a unit circle. What are the advantages? Advantage is that it's one of the application I say. Suppose I want to solve a Laplace equation or Poincare equation in upper half plane or left half plane, let's say, because I've given you an example of a left half plane. So please understand what I'm doing is that I have my left half plane and I translate this half plane into unit circle or circle. Into a circle. Now, if I want to solve a Poincare equation, which is day2u by dx2 plus day2u by dy2 equal to fxy with boundary condition. Then in the left half plane, then which formula is given because coming from here to that formula, then I will try to find the solution of this equation when I take my control map which translate left half plane into unit circle. Then please understand me, in the new coordinates, it is d2 by Day-2 plus Day-2 by Day-2 is equal to EFZ, that thing, and on fx5. That x will be coordinated, I write Day-2. So my form remains the same. Now my domain of the left side is translated into a circle. Now I know that in the complex analysis, there is a popular Poisson integral formula. Poisson integral formula which connect. What it says is that the Poisson is for a circle that u r theta is given by 0 to 2 pi pi r square minus capital S upon r square minus 2r cosine theta minus phi plus small r square and d phi. What I mean to say is this is well-known formula. That is, to find the solution of Laplace of Poisson equation, one can use this formula and solution in the circle can be obtained. Once I get the solution in the circle, then by taking the inverse transformation, the solution on the what we call your left half plane can be done. Friends, I'm talking about left half plane, but same thing can be talked about upper half plane or lower half plane. This is one application of the what you call this transformation. I just take another application, but before that, let me complete my thing. So let me take first, I define what we call a fixed point. So what we call fixed point of bilinear transformation. So suppose I have my W equal to AZ plus B upon CZ plus D. This is my bilinear transformation. Z is called a fixed point under W equal to Fz if Z equal to Fz. So what I'm meaning to say is that my Z will be a fixed point if Z equal to AZ plus B upon CZ plus D. Or I have CZ square plus DZ equal to AZ plus B. Or I have CZ square plus B minus AZ plus B equal to 0. So this is my what you call transformation which gives me that a quadratic equation, and that is if Z is a fixed point, then this quadratic equation should be satisfied. What it tells me is that for every bilinear transformation, there are two fixed points. There are two fixed points. That's what it says. For the sake of example, if I take the transformation W equal to 2z minus 1 upon z minus 1, I want to find the fixed point of this transformation. Now, when I want to find fixed point, that z equal to 2z minus 1 upon z minus 1, or z square minus z equal to 2z minus 1, or z square minus 3z plus 1 equal to 0. And as you know that I can find the root of this, which is nothing but 3 plus under root 9 minus 4 upon 2. And so my fixed points are 3 plus minus root 5 upon 2. So that's what it is. Now, if I take another example, then I want to find a bilinear transformation. Here, so find bilinear transformation where 1 goes to 2, 1 I goes to I, and minus 1 goes to minus 2. So I is one of the fixed point. You can see I is one of the fixed point. So the solution of this will be, suppose W equal to AZ plus B upon what we call CZ plus D. To make my life easy, I write alpha Z B plus beta upon Z plus gamma. So I write this way. Now my 1 goes to 2, meaning is that by 2 equal to A plus B C plus D equal to nothing but alpha plus beta upon 1 plus gamma. So I don't take this path, I take this path. And what I get is from this is 2 plus 2 gamma equal to alpha plus beta, or alpha plus beta minus 2 gamma equal to 2. This is my one equation. My second equation will be that minus 1 goes to minus 2. That is minus 2 equal to minus alpha plus beta upon z, which is what we call minus 1 plus gamma. So that's what I get. And this gives me plus 2 minus 2 gamma is equal to minus alpha plus beta. Or what I get is alpha plus, I get from this beta minus alpha plus 2 gamma equal to 2. I hope everybody is getting. So I get these two equations. Now what you see is that these two equations, I can see that when I add, what I get is, when I add them, what I get is that 2 beta equal to, because beta remains, alpha cancel out, gamma cancel out, 2 beta is equal to 4, or beta equal to 2. My beta is okay. The moment I get beta, now I have my equation H, alpha plus minus 2 gamma is equal to 0. Because beta is 2, so when I put beta equal to 2, this 2 cancel with this 2, and what I get is alpha minus 2 gamma equal to 0, or gamma equal to alpha by 2, or alpha equal to 2 gamma. So my transformation are known to me with of freedom of parameter, or one constant, one parameter gamma. So my transformation become no, I have to use I goes to I. From there I can get. So I put that first. So I have my W equal to what you call alpha is uh, uh, my alpha is 2 gamma. So 2 gamma z plus beta, which is 2 upon z plus gamma. But it says that my I goes to I. So my I equal to 2 gamma I plus 2 upon z plus gamma. This becomes I. This becomes I. And then simplify it, but that is minus 1 plus gamma I equal to 2 gamma I plus 2. And out of it, I get that my gamma I equal to minus 3. Or my gamma becomes from here, my gamma becomes what you call 3I. My gamma becomes 3I. So my transformation H, W equal to 2 times 3IZ plus 1 upon Z plus 3I. That is the transformation which I get out of it. So friends, what I mean to say is, by doing simple analysis, a bilinear transformation can be used. Now I want to tell you another application, which is most of mathematicians do, and in electrical and electronics engineer also that kind of analysis done. That is called stability analysis. What is the stability of a system, of a problem? Is that you have a system which is behaving quite properly, but you want to know how sensitive the system is. So you give slight perturbation to the system. And when you give slight perturbation to the system, if a system behaves properly, we say it is stable. If there are problems, then you have to discuss why it is doing so. And but I can say the system is not unstable, then what kind of instability is there which can be discussed. So one of the problem in the what you call in stability analysis, that you have to find roots of a characteristic polynomial, which are nothing but eigenvalue polynomial. And what it's not simple polynomial, because there are different parameters involving in the system. So you have parametric equation of the polynomial. Now you want to know whether the system, what value of parametric it will be stable. Generally, this should be having roots within the unit circle. That is, their magnitude is less than 1. So as time goes by, the magnitude becomes smaller and smaller, and this doesn't create any problem. That's what the stability is. But now finding this, whether these roots are within the unit circle or not, it is a problem. So what we do is that we take conformal transformation, which transform the unit circle into upper half plane, or let's say left half plane. That is much easier. So I take left half plane. So I transform the unit circle into left half plane. Then the moment I transfer the left half plane, the interior of the unit circle goes to the left side of the coordinate system. And what will happen in that case? In that case, if your roots are lying in the unit circle, then transformed polynomial should have all negative real part, because negative real part will be in the left half plane. Because any number which is coming in the left half plane will be having negative part. And hence, judging whether the real parts are negative or not is rather easy than seeing that whether the roots are lying inside the unit circle or not. So that is one of the criteria, which is Rath criteria, we say Rath-Hurwitz criteria, which is applied when what we do, Rath-Hurwitz criteria. That is called the Rath-Hurwitz criteria. It says that transform the system into upper half plane, left half plane, and check whether your roots are negative or not. The condition is given when the roots will be negative. And so very easily you can check whether the system is stable or not. So this much from my side. Thank you very much. If you have any question, please don't hesitate to ask me. I will be glad to answer if I know.
Anybody
Hello,
has
madam.
any question, please? Okay. Thank you, sir, for enriching us. Your experience and expertise of many years was pouring out of your words, sir. We truly appreciate you that you always spend your time in gracing our various occasions. Thank you, sir. Thank you once again, sir, for a
Thank you.
wonderful lecture.
Thank you very much, madam.
Welcome, sir. Thank you, everyone. Please keep your camera on to capture the lovely moment. Everyone, please keep your cameras on. Window plus print screen. Thank you. Thank you, everyone. Thank you, sir.
I am leaving now.
Okay, sir. Yes, guys.